Talk is on TopK personalized PageRank queries on large graphs, and it's going to be presented by Zhewei Wei.
All right. Hi, everyone. Today I'll talk about an algorithm that compute TopK personalized page ranks with precision guarantees. So this joint work with Xiaodong He, Xiaokui Xiao, Sibo Wang, Shuo Sang, and Jirong Wen. My name is Zhewei Wei. I'm an associate professor from Renmin University. So I assume that most of you are familiar with the personalized page rank, or PPR, but let me refresh your memory anyway. So given a source node S on a graph, and we start a random walk with start from S, such that at each step, with probability alpha, it returns to the source node S. And with probability 1 minus alpha, it moves to a random neighbor. So the PPR vector pi S is just the stationary distribution of the random walk. So we're interested in computing the TopK PPR queries. That is, given a source S, return the top K node set with the highest PPR values. So in this case, the top 5 nodes set of this source S is simply the reddish nodes, that is 1, 2, 3, 5, and 8. And TopK PPR queries has a lot of applications. For example, personalized web search, graph clustering, and recommendations. And it's usually the bottleneck of computation in these applications. And due to its importance, there has been a lot of work trying to improve the running time or the accuracy of the TopK PPR queries, and at least some of the exact and approximate methods here, because we are going to compare our algorithm with them. Since I don't have time to go through these methods, so let me just say this. They suffer at least one of these following drawbacks. They either require pre-processing and large index, which makes them unable to run on dynamic graphs, or they are unable to return the exact TopK node set, or they offer slow query time on large graphs. And therefore, we propose the TopPPR algorithm. What's new about our algorithm is that we take in a new parameter row from 0 to 1, and we answer TopK PPR queries with the precision at least row with high probability. The precision is just defined as the true TopK nodes in the answer divided by K. So that means if we set row equals to 1, then essentially you have to return the exact TopK node set, which is very challenging. But what's more challenging is that we want to do it without pre-processing or indexing. And our query bounds depend on this parameter gap row, which is essentially the gap between the row case and the K plus 1 largest PPR values. And if we set row equals to 1, then this essentially means that the exact PPR query depends on the gap between the case and the K plus 1 largest values, and that which sort of makes sense. So our algorithm combines 3 existing techniques. The forward search, which sort of push the probability from the source node S to other nodes, and the backward search, which sort of push the probability from a targeting node T back to other nodes. And of course, the random walk sampling, which simply sample random walks and use Monte Carlo algorithm to estimate the PPR values. And this is our estimate formula. And we are doing this in a non-trivial way, because otherwise this wouldn't be a sigmoid paper, right? But I don't have time to go through the details, but let me give you the major challenge. That is, that's in the backward search. Because if you recall, we have to perform backward search on the target node T. But the TopK PPR queries only give you a source node, which essentially means every node in the graph is a target node. So the question is, how do we perform backward search on all nodes efficiently? And the answer is, well, we don't. We divide the graph into 3 sets. The TopK sets, which consists of nodes that we are confident to classify as TopK node. And non-TopK nodes, which, well, we are classify them as non-TopK node. And the candidate set, these are the nodes that we are not sure about, and we are going to compute backward search only on this node. But how do we do the classification? Well, we use confidence bound computed by the empirical Bernstein inequality. And using this confidence bound, we can iteratively move the nodes from the candidate set to top K or non-top K set, which makes the candidate smaller, and we can perform deeper backward search on the candidate set and get better and better confidence bound. And whenever the top K set reaches the size of row K, then that means, okay, our precision is at least row. And we can return the top K set as our results, and that would guarantee a precision of at least row. So for experiment, we compare our algorithm with the state-of-the-art exact and approximate top K PPR algorithm on 4 real-world graphs, the largest one being Twitter, and it consists of 1.4 billion edges. And for exact PPR queries, as you can see, we outperform the closest competitor by 2 orders of magnitude for k equals to 1 to 1,000. But keep in mind, it's not entirely a firefight, because while these 2 algorithms can return the exact PPR query in the exact order, while we only can achieve an DCG of 1.99999, only close to optimal. And for approximate algorithm, while we outperform the state-of-the-art algorithm that is 4 plus in terms of query time. And do keep in mind, 4 plus is the index-based algorithm. It uses index roughly the same size of the graph, and it requires pre-processing, while we don't. So, which makes our algorithm perfect for dynamic graphs. And also, we can provide better precision due to our theoretical precision guarantee. So, in conclusion, we present an algorithm TopPPR, which offers theoretical guarantee on precision of the results, and we can compute exact and approximate algorithm top K queries without processing or indexing. And we achieve nice results on real-world graphs. Thank you.
That's nice. Any questions on this? Yep. Could you go to the microphone, please? I don't know where the shortest path is. That's a good question.
So this seems like it's inspired by some bandwidth focusing mechanisms that have been used for some other algorithms. I think BFS, maybe shortest paths with ranking edges by weight and dividing them up into bounds. I saw that you had effectively a pivot region, some things that were in a clique on the top, some that were on the bottom, and some that were in the pivot. And I'm wondering how related these techniques are to focus on a subset of the problem at a time.
Right. Actually, quite related, because as you can see, we use the confidence bound sort of in the multi-arm bandits theory, right? And so our assumption is depend on this graph is sort of a power law graph, which makes the personalized page rank uneven. Otherwise, you can't do anything about it, because if all these personalized page ranks are the same, it's 1 over n, then you can't do anything about it. Right? There's no top K, because everything is the same. So, but if the graph is power law, then it basically says the personalized page rank also follows power law, and then the tricks can kick in. Yeah.
Any more questions? All right, great. So, thanks.